What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. On Mars sits a machine that made oxygen from the planet's air. It is called MOXIE. It rode to Mars inside the Perseverance rover, and over the course of 16 runs, it produced a total of 122 grams of oxygen. At its best, it made 12 grams in an hour, with a purity of at least 98%. This was the first time a machine on another world had taken a local material and turned it into a resource that future explorers could use to survive, and perhaps to leave. That is a triumph. It is also a warning about scale. Some studied Mars ascent vehicles would need roughly 33 to 50 metric tons of propellant. The exact amount depends on the vehicle, the route, and the architecture, but in designs that burn methane and oxygen, most of that propellant mass can be oxygen. A small experiment proved that the chemistry works. A crew would need an industrial system that works hour after hour through cold, dust, seasonal pressure changes, maintenance, storage, and every failure that has not yet happened. The difference between 122 grams and tens of tons is not just a bigger machine, it is a chain. Power has to reach the compressor. Carbon dioxide has to enter without choking the system with dust. Oxygen has to be separated, checked, cooled, and stored. Valves have to keep sealing. Sensors have to keep telling the truth. Spare parts have to fit. The tanks have to remain safe. And the whole process may need to finish before the crew places its life on the result. That gives us the first answer. The return flight cannot be treated as the final chapter of a Mars mission. It has to exist as a working possibility before the crew leaves Earth. NASA has landed many robotic spacecraft on Mars, but no mission has ever attempted to lift from the Martian surface and reach orbit. Current studies still compare basic choices. Should a landing vehicle also become the ascent vehicle, or should the crew arrive beside a separate rocket? Should all propellant come from Earth, or should some of it be made on Mars? Should an ascent vehicle wait on the surface before the crew arrives, already checked and fueled? Or should the mission accept the added chain of producing its fuel after landing? None of those choices is a flight plan yet. They are branches in an architecture that is still being defined. But every branch reveals the same thing. Reaching Mars and returning from Mars are not mirror images. Earth gives a launch vehicle an atmosphere, oceans, factories, launch pads, tracking networks, repair crews, hospitals, roads, replacement parts, and a planet full of people who can walk up to the machine. Mars gives the return vehicle whatever the mission carried there, whatever it successfully made there, and whatever the crew can still repair. If seeing Mars through the machinery that must bring a crew home is your kind of exploration, you can subscribe, and we will keep following the evidence together. The dream of Mars often begins with a footprint. The engineering of Mars begins much earlier, with a list of conditions that must still be true years later. The crew must arrive healthy enough to work. The landing system must deliver not only people, but the mass of the habitat, power supply, food, tools, shielding, and return equipment. The habitat must keep a small Earth alive inside a pressure vessel. Water must circle through bodies and machines without becoming contaminated or disappearing too quickly. Air must remain breathable, even as people, plastics, electronics, microbes, and dust change its chemistry. Food must keep its nutrition long after it was packed. Power must survive the surface environment. The crew must diagnose problems, while a question to Earth and its answer may take 44 minutes. Then the ascent system must work after wading through all of it. Only after that can the crew begin the journey home. This is why the hardest part of a Mars mission may not be one spectacular maneuver. It may be keeping every ordinary requirement inside a recoverable boundary for long enough. A pump can work today and still be unsuitable if it wears out before departure. A water processor can recover almost everything and still lose too much over hundreds of days. A food package can remain safe and still lose vitamins. A person can remain conscious and still lose enough strength, balance, or bone to make repair and emergency movement harder. A propellant plant can make oxygen and still fail to make enough, store enough, or prove that enough is ready. Mars turns reliability into a rate. To see why, we have to replace the image of one voyage with the geometry of two moving planets. Earth and Mars do not sit at a fixed distance. They orbit the Sun at different speeds. Earth completes its path more quickly and repeatedly catches up with Mars, then moves ahead. A spacecraft does not usually aim for where Mars is when it launches. It enters an orbit around the Sun, chosen to meet Mars where the planet will be months later. That geometry creates favorable opportunities, but it also creates a clock. If the crew reaches Mars and something important fails, Earth is not a nearby harbor that happens to be far away. The planets may be moving into a configuration that makes an immediate return enormously expensive or impossible for the available vehicle. Mission designers study different ways through this geometry. A long stay or conjunction class mission uses relatively efficient transfers and can keep a crew near Mars for about 500 days, while the planets move into a favorable arrangement for the return. In many studies, the complete journey lasts more than 1,000 days. A shorter stay, opposition-class mission can reduce the time on Mars, but it demands a more energetic route. Some studied versions last around 850 days and may include only about 30 days at the destination. They can require far more capable propulsion and may introduce difficult flyby geometry. These are examples, not a schedule for the first crew. Their value is that they expose a trade that cannot be wished away. Time, propulsion, mass, radiation, surface work, and return opportunity are connected. Saving time can cost energy and hardware. Saving propellant can cost months. Adding surface time can improve science and justify the landing. But it also asks the habitat, bodies, food, power system, and ascent vehicle to keep aging. The moon teaches a different intuition. A spacecraft can reach the moon in days. Radio commands cross the gap in a little more than a second. Emergency plans remain brutal, but Earth is close enough for continuous conversation and for return paths measured in days. Mars changes both facts, The one-way radio delay varies from about 3 to 22 minutes as the planets move. At the largest delay, a crew that asks a question will wait about 44 minutes for the earliest possible answer, even if a person on Earth understands the problem instantly and replies without hesitation. That is not a slow telephone call. It is a transfer of responsibility. On the International Space Station, a strange sound, a sensor reading, or a failed component can bring specialists into the conversation almost immediately. Teams on the ground have full rooms, large databases, hardware replicas, and colleagues across different disciplines. For Mars, those people remain valuable, but they cannot be the hands that stabilize a fast event. The crew and the vehicle must detect more, understand more, and act safely before Earth can respond. At certain alignments, the Sun also lies near the radio path between Earth and Mars. Plasma around the Sun can corrupt communications, and robotic Mars missions already reduce commanding during these conjunction periods. A human mission would plan for these intervals. The important point is not that all contact vanishes for a fixed dramatic scene. It is that autonomy has to be designed into ordinary operations from the beginning. This is the deeper meaning of distance. Kilometers are only the first layer. Distance becomes delay. Delay becomes onboard authority. Orbital motion becomes a waiting period. A waiting period becomes food age, component wear, radiation dose, exercise time, and a deadline for making propellant. The mission clock begins before the crew sees Mars. It also begins before the crew leaves low Earth orbit. A human Mars vehicle may be too large to launch as one complete machine. Different studies assemble vehicles, propellant, habitats, or cargo through several launches. Some elements travel slowly without people. Others wait in orbit. A crew boards only after the larger system is checked. This distributes one launch into a campaign. The advantage is that no single rocket has to carry everything at once. The cost is that every connection becomes part of the mission. Docking ports must align. Fluids or power may need to transfer. Hardware launched months apart must remain compatible. One delayed element can age the elements already waiting. Pre-deployment changes the order of risk. Cargo can take an efficient route that would be too slow for people. A habitat can land before the crew. A power system can start. A rover can survey the area. An ascent vehicle can report its health. Each successful step lowers uncertainty before humans commit. But a pre-deployed system is also an unattended system. Mars wind and dust move around it. Temperatures cycle. Batteries age. Lubricants and seals experience time. Software waits for commands through a changing communication geometry. A machine that reports green status on landing must still prove that it can remain green until the crew arrives and until the crew departs. This creates a decision that is easy to miss in artwork. At what point does the mission become committed? Before departure from Earth orbit, there may be ways to stop. A crew can remain home if a cargo lander fails. It can wait if an ascent plant has not produced enough propellant. It can replace a suspect module while people and industry remain nearby. Once the interplanetary burn is complete, many convenient aborts disappear. The vehicle cannot turn around like an aircraft. Its motion around the sun, available propellant, life support, and the positions of the planets define what paths remain. Mission designers therefore try to move uncertainty to the side of the commitment where people are still close to Earth. They test hardware, they carry reserves, they pre-position critical assets, they verify. This is not caution added after the adventure. It is how the adventure becomes permissible. The result resembles a chain of locked doors. One should not close until the next region contains enough verified capability. Earth launch closes access to ordinary recovery. Interplanetary injection closes many rapid return options. Mars entry closes the option to remain in orbit. Surface departure closes access to the habitat. Earth entry commits the crew to atmospheric return. At each door, the question is not whether every risk has vanished. It is whether the system on the other side has enough margin, evidence, and fallback paths to carry human life to the next door. Radiation begins consuming one of those margins as soon as the vehicle leaves the strongest protection of Earth's magnetic environment. In November 2011, the Mars Science Laboratory left Earth carrying the Curiosity rover. Tucked inside the cruise stage was an instrument called the Radiation Assessment Detector, or RAD. For most of the 253-day journey, through a path totaling about 560 million kilometers, RAD counted energetic particles inside the spacecraft. Those numbers need careful interpretation. The 560 million kilometers describe the spacecraft's curved cruise path, not a simple ruler placed between the planets. The detector also sat inside a particular spacecraft with a particular distribution of shielding. It was measuring one real journey during one part of the solar cycle. It was not carrying a human body, and it was not predicting the exact dose of a future crew vehicle. But it gave mission planners something they had never possessed at that detail before. It measured the radiation environment along a path to Mars from inside the spacecraft that was actually traveling there. To understand the measurement, it helps to separate three ideas that are often compressed into the single word dose. The detector first records energy deposited by particles in material. That absorbed dose tells us how much energy arrived per unit of mass. Biological effect depends on more than energy alone. A high-energy heavy ion can leave a dense path of damage through cells, while another kind of radiation can spread the same energy differently. Dose equivalent applies a quality factor intended to reflect those differences in biological effectiveness. Even that number is not a personal forecast. Risk depends on which tissues are exposed, age, sex, individual biology, the timing of exposure, and uncertainties in how deep space particles affect humans over long periods. A detector can measure the field far more directly than it can predict a particular person's future health. This is why the units matter and why they do not settle the argument alone. A rate such as millisieverts per day allows mission planners to compare routes, shielding, and time. It does not mark a day on which a crew becomes suddenly unsafe. The hazard accumulates and varies. Solar activity complicates the pattern. When the sun is more active, its magnetic influence can reduce some of the galactic cosmic rays reaching the inner solar system. The same active sun can also produce energetic particle events. A quiet period can mean fewer solar eruptions, but a stronger galactic background. There is no single season when all radiation becomes favorable. Shielding also refuses to behave like a simple wall. A very energetic ion can pass through material and strike nuclei along the way, producing secondary particles. Thickening the wall can reduce exposure, but the material and geometry affect the result. Hydrogen-rich substances are attractive in many concepts because their light nuclei tend to create a different secondary field than heavy metals. Water, food, waste, and fuel may therefore become movable protection. The same water that keeps a crew alive can line a sleeping area or storm shelter. Supplies consumed later in the mission can begin in positions that add shielding, but as they move and disappear, the protection changes. Waste may replace some of that mass if it can be stored safely. A shield becomes part of logistics. The storm shelter illustrates the design philosophy. It does not need to enclose the entire habitat at maximum thickness. It concentrates available mass around a smaller volume, where the crew can remain during an elevated solar event. Forecasting and onboard detectors provide warning. Procedures move people and essential supplies into the protected space. Galactic cosmic rays are harder to handle with short shelter visits because the background continues through the voyage. Reducing transit time can reduce accumulated exposure, but a faster trip may demand more propulsion, power, or propellant. Adding shielding raises mass. Artificial gravity concepts may improve health, but add structure and operational complexity. Radiation returns us to the architecture instead of yielding one isolated fix. The biological problem is also a maintenance problem. Radiation can affect electronics, detectors, materials, and stored biological supplies. Critical computers can use error correction and redundant channels. Components can be shielded or selected for tolerance. Software can detect a flipped bit before it becomes a wrong command. Again, resilience comes from expecting small disturbances and preventing them from coordinating into a larger failure. The crew lives inside the same philosophy. Health monitoring looks for change early enough that work, medication, shelter use, or mission plans can adapt. The goal is not to make a human body invulnerable. It is to preserve function and keep risk within an accepted boundary through the complete round trip. The average dose equivalent rate during that cruise was about 1.84 millisieverts per day under those conditions. After Curiosity landed, RAD continued measuring at the surface. During its early surface campaign, the reported average was about 0.64 millisieverts per day. A smaller number on the surface does not mean the surface is safe by default. Mars places the planet itself beneath the detector, so half the sky is blocked by the ground. The atmosphere, thin as it is, removes or transforms some incoming particles. Local terrain can block another part of the sky. In 2021, researchers reported a direct example from a period when Curiosity sat close to a butte. RAD measured a reduction because the rock mass screened part of the incoming radiation. That is an important turn. Radiation is not only a number assigned to a planet. It depends on time, solar activity, the direction and energy of particles, spacecraft materials, the arrangement of mass around the crew, and where the crew works. The most persistent background comes from galactic cosmic rays. high-energy atomic nuclei that arrive from beyond the solar system. They are difficult to stop because many carry enough energy to pass through substantial material. When they strike shielding, they can also produce showers of secondary particles. More mass can help, but the kind and placement of that mass matter. Materials rich in hydrogen, including water and some polymers, can be useful because they tend to break up these particles with fewer damaging secondary fragments than very heavy metals. The sun creates a different hazard. Solar energetic particle events can send large numbers of particles outward over a shorter period. These events vary enormously. A vehicle can include a storm shelter, a small region surrounded by supplies such as water and food, where the crew can gather when space weather monitoring indicates elevated risk. The two hazards demand different habits of thought. A shelter may greatly reduce exposure during a solar event. Galactic cosmic rays create a continuous design problem through much of the mission. Their biological effects also carry uncertainty because the particle mixture and low dose rate differ from many medical and terrestrial exposures. Scientists use measurements, models, cell studies, animal research, astronaut data, and epidemiology to estimate risk. The estimates are not the same as watching a meter and knowing one person's future. So the honest statement is neither that radiation makes Mars impossible, nor that it has been solved. It is measured, serious, variable, and connected to vehicle mass and mission time. This is where the mission clock returns. A shielding decision affects launch mass. Launch mass affects propulsion and assembly. Propulsion affects transit time. Transit time affects dose. A longer surface stay adds exposure, but the surface offers access to mass that can become shielding. Water tanks can be placed around occupied areas. Supplies can be arranged around a storm shelter. Habitats might be covered with processed regolith or placed beside natural terrain, but every such concept creates construction, verification, access, and dust problems of its own. No wall deletes the problem. Good architecture moves the dose and risk toward a range that can be accepted, monitored, and managed. The crew also changes while this invisible rain continues. During the cruise, the travelers may spend months in microgravity. Without a constant downward load, the body begins reallocating resources. Muscles that once held the body upright do less work. Weight-bearing bones lose mineral. Fluids shift toward the head. The cardiovascular system no longer has to push blood upward against Earth's gravity in the same way. Balance organs and the brain recalibrate to a world in which up and down are choices rather than fixed directions. Exercise is one of the strongest countermeasures available. Space station crews use resistance machines, treadmills, and cycling equipment to load muscles and bones and maintain cardiovascular capacity. Nutrition, medication, monitoring, and personalized plans also matter. These measures reduce harm, but they do not make months of microgravity biologically identical to life on Earth. NASA summarizes average mineral density loss in weight-bearing bones during spaceflight at about 1 to 1.5% per month, though people vary and countermeasures matter. The statistic is not a countdown to a uniform injury. It is evidence that the body is continuously adapting to the force environment it actually experiences. Then the crew reaches Mars, and the direction of adaptation changes again. Surface gravity is about 38% of Earth's. That is enough for objects to fall, for dust to settle, and for a person to feel weight. It may make movement easier than it would be after landing on Earth. But no human has lived for months or years in Mars' gravity. We do not know whether 38% is enough to maintain bone, muscle, cardiovascular function, vision, immune regulation, and coordination over a long stay. We have data from microgravity and brief transitions through partial gravity during parabolic flights and training. We have animal studies and mechanical models. We do not have the direct, long-duration human measurement that would settle the question. That genuine unknown matters because the crew does not arrive at a clinic. It arrives at the most demanding work site humanity has imagined. Landing may expose the body to changing acceleration, vibration, noise, and a rapid transition from weightlessness to partial gravity. After touchdown, people may need to leave seats, verify pressure, respond to alarms, unload equipment, inspect systems, and perhaps perform repairs in suits. A person can be medically stable and still have reduced balance, strength, or fine motor control at the exact moment the mission asks for it. The same issue returns at departure. The ascent vehicle may impose several times Earth's gravity for a short interval. Months later, the crew must enter Earth's atmosphere and return to a full gravity field. Safe return, therefore, includes more than a heat shield and parachutes. It includes preserving the ability to tolerate and recover from the final transition. Countermeasures have their own machinery. A resistance exercise device needs structure to push against, moving parts, sensors, and room for a person to use it safely. A treadmill needs restraints because the runner would otherwise float away. Exercise creates heat, humidity, carbon dioxide, noise, and wear. It consumes crew time and may require maintenance on equipment whose failure slowly reduces health margin. This is a pattern Mars repeatedly exposes. The solution to one biological problem enters the habitat as a mechanical system and creates loads for other systems. Medical planning faces the same conversion. On Earth, a symptom can lead to a specialist, a laboratory, advanced imaging, a pharmacy, or a hospital. A Mars crew carries selected capabilities and reaches Earth experts through delay. Mission planners have to decide which conditions the crew can diagnose, which treatments are practical, and which events remain beyond the available care. Carrying a device is not the same as carrying a capability. Someone must know how to use it. Supplies must remain sterile and within shelf life. Batteries must charge. Sensors must calibrate. Procedures must fit the actual crew and cabin. A medical officer may also be the patient, which means knowledge has to be distributed. This does not require imagining a dramatic surgery on Mars. Ordinary health can consume the system. A dental problem, skin injury, infection, sleep disruption, motion sickness, or repetitive strain can reduce work capacity. Small conditions matter when the same 4 people operate every critical function and no replacement arrives. The crew must also protect exercise and recovery time against the mission's endless appetite for labor. A delayed repair can steal a workout. A long surface activity can change sleep. Repeated schedule erosion can turn a strong countermeasure into a plan that exists on paper, but not in daily life. Human performance is therefore a reserve like water or power. It can be spent faster than it is restored. This is why health cannot be placed in a separate medical chapter. It is part of vehicle performance. The crew is a repair system, a decision system, a sensing system, and the only medical team available at Mars. Their physical capability changes the meaning of every redundancy plan. The first major task awaiting that crew is one that robotic missions have made look almost familiar: landing. Mars has received a remarkable procession of machines. Viking descended under parachutes and rockets. Pathfinder arrived inside a cluster of airbags. Spirit and Opportunity bounced to the surface. Curiosity and Perseverance were lowered on cables beneath rocket-powered descent stages. Phoenix and Insight fired engines for their final approach. Each success enlarged the set of things engineers know how to do. None of them proves that a crew habitat can simply repeat the maneuver at a larger scale. The Perseverance rover had a mass of a little more than 1 metric ton by itself. Human Mars entry studies examine payloads around 20 metric tons, and a complete campaign may need several large deliveries. That change is not like moving from a small truck to a larger truck on the same road. The road itself changes under the mass. Mars has an awkward atmosphere for landing. It is thick enough that a vehicle arriving at interplanetary speed slams into gas and creates intense heating. A heat shield can use that drag to shed enormous speed. But the air near the surface is less than 1% of Earth's average pressure. It is too thin for a conventional parachute to bring a human-scale payload gently to the ground by itself. The vehicle has limited altitude in which to solve the problem. It must enter at the correct angle, survive heating, remain stable, navigate toward a landing zone, deploy or use a large decelerator, and then transition to powered flight while still moving quickly. The larger vehicle may not fit inside the shapes used for robotic capsules. Engines firing into a supersonic flow create interactions that are difficult to reproduce at full scale on Earth. Plumes strike the surface and can throw dust and rocks. The lander must avoid hazards while carrying pressure vessels, people, and systems that cannot tolerate a hard impact. The sequence begins before the atmosphere. Navigation has to deliver the spacecraft to a narrow corridor at the correct time, speed, and orientation. Too steep, and heating and deceleration can become excessive. Too shallow, and the vehicle may fail to lose enough energy, or may leave the atmosphere again. The entry shape trades heating, stability, steering, and internal volume. During hypersonic flight, radio signals can be affected by the hot ionized gas around the vehicle. The crew cannot expect Earth to guide each second anyway. Onboard navigation combines inertial measurements, radar, cameras, and stored terrain information, depending on the design. The system must know where it is, where safe ground lies, and how much energy remains. Large landing systems may use lift to travel across the atmosphere and correct their range. A deployable or inflatable decelerator increases area without requiring the entire shield to fit inside a conventional launch fairing. Supersonic retropropulsion uses engines while the vehicle still moves faster than sound. Each method moves risk into different materials, deployment events, control laws, and tests. Then the ground begins influencing the vehicle before contact. Radar sees terrain, cameras compare patterns, engines push gas downward into a low-pressure environment. Plumes interact with one another and with the surface. Dust and fragments can strike the lander, nearby cargo, or equipment placed in advance. Landing legs or another support system must tolerate slope and uneven ground. A robotic mission can accept landing dispersions and drive toward a target later. A crew landing beside a pre-positioned habitat or ascent vehicle has tighter consequences. Surface range consumes rover power, time, and life support. Rough terrain may block a route. A pressurized rover can extend reach, but then the rover joins the list of systems that must already be available and verified. Landing precision is therefore not only a navigation score, it controls how much surface infrastructure can function as one base. The crew's role during descent also demands restraint in storytelling. Future explorers may monitor and command parts of the sequence, but exact controls depend on the unchosen vehicle. Automation will likely handle changes too fast for delayed Earth support. We should not imagine a pilot staring through a window and steering by sight. The honest drama lies in the vehicle interpreting measurements correctly, while every option narrows. NASA studies several approaches. Some use rigid lifting bodies that can steer through the atmosphere. Some examine large inflatable or deployable decelerators. Powered descent with retro rockets appears in many concepts because parachutes proven on smaller missions do not scale cleanly to the needed mass. These are active engineering paths, not a single vehicle waiting for a launch date. The distinction matters visually. A beautiful rendering of a giant craft descending over red terrain is not a photograph of a solved system. It is an argument in hardware form. The shape, engine placement, tanks, landing legs, and sequence each represent assumptions that still have to survive testing. Landing also controls what happens afterward. A lower sight gives the vehicle more atmosphere through which to slow down, but a mission may prefer a sight for science, access to water ice, sunlight, terrain safety, or communication. A high-latitude site may offer more accessible ice but lower temperatures and different sunlight. A site with natural shielding or interesting geology may present rough terrain. Every advantage arrives attached to another subsystem. Cargo changes the risk. A mission can send power units, a habitat, supplies, and an ascent vehicle before the crew. Robotic systems can verify some functions and build reserves, but every pre-landed element creates a navigation requirement. The crew must land close enough to reach it safely, while large vehicles need separation, so one landing does not damage another. Surface mobility, then, becomes part of the survival architecture. If a cargo lander misses its target by too much, the equipment may exist on Mars and still be useless to the crew. If a power system lands successfully but cannot connect to the habitat, electrical capacity on a manifest does not become electricity in the cabin. If a return vehicle arrives first, it has to survive the surface while waiting. This is the first place where the glamorous milestone and the ordinary chain collide. Touchdown is not the end of landing. Landing is complete only when the delivered systems can find, connect, start, verify, and support one another. Then, a hatch opens onto an environment that offers almost nothing a human body can use directly. The Martian atmosphere is about 95% carbon dioxide. Oxygen is only a trace. Surface pressure varies with altitude, weather, and season, but it is generally around 0.6% of Earth's sea level pressure. Exposed liquid water is unstable under most surface conditions. Depending on temperature and local pressure, it tends to freeze, boil, or disappear into the dry air. A human outside therefore needs a pressure suit that supplies oxygen, removes carbon dioxide, controls temperature, manages humidity, allows movement, and resists abrasion. A human inside needs the habitat to perform the same basic work continuously for everyone. Calling the habitat a home is emotionally right and mechanically incomplete. It is a factory for a tiny atmosphere. It is also a structure under continuous load. Inside, gas pushes outward. Outside, the thin atmosphere pushes back only slightly. Every hatch, window, cable passage, fluid line, and joint interrupts the pressure shell. A leak can be sudden or small. A large leak demands rapid isolation. A small leak may appear first, as a slow change in pressure or a growing demand on makeup gas. Locating a small leak inside a habitat full of fans and machines can be difficult. Sensors can divide the base into zones. Valves can isolate modules. Acoustic methods may hear high-frequency flow. The crew can compare pressure trends. The architecture can include more than one habitable volume, so a damaged section does not become the entire mission. Compartmentalization costs mass and complexity. Extra hatches add seals. Separate volumes need ventilation and emergency supplies. Yet one large open room creates a common failure space. The correct balance is another system's choice. The habitat atmosphere itself is a design decision. Earth's sea level pressure is familiar to the body, but a lower pressure atmosphere can reduce structural loads and change suit operations. Oxygen concentration and total pressure have to be chosen together so people receive enough oxygen without creating unacceptable fire or decompression risks. Transitioning between a habitat and a suit may require time to manage dissolved nitrogen in the body, depending on those pressures and gas mixtures. The point is not to select a cabin atmosphere here. It is to notice that pressure, structure, fire, suit design, and daily schedule cannot be optimized independently. Temperature control shows the same connection. Mars can be intensely cold, but the habitat also has to reject heat from people and equipment. Insulation slows unwanted heat flow in both directions. Radiators need a view of the environment and surfaces that maintain their thermal properties. Dust on a radiator can change performance. A greenhouse or oxygen plant may add large heat loads. The base can be cold outside and overheating inside. Windows offer light, orientation, and a view of Mars. They also interrupt shielding and insulation. Cameras and displays can provide views without a large opening, but they are not psychologically or operationally identical. Design has to value human needs without pretending they have no mass or risk. The best habitat may look less cinematic than the most popular rendering. It may have few windows, layered equipment around occupied spaces, external radiators, protected connections, separated modules, and work areas arranged around maintenance access. Beauty in that environment is a system the crew can understand. Walls hold pressure against the near vacuum outside. Pumps move air through spaces where still pockets could allow carbon dioxide or heat to accumulate. Molecular sieves or other systems remove carbon dioxide. Filters capture particles. Beds and catalysts remove trace chemicals released by plastics, electronics, cleaning agents, experiments, and human metabolism. Water condenses from breath and sweat. Heat exchangers move metabolic and electrical heat toward radiators. Sensors compare the cabin to allowed ranges. Microbial monitoring looks for an ecosystem that has shifted in the wrong direction. All of those processes share boundaries. A fan failure is not only a comfort problem if it reduces ventilation around a carbon dioxide removal path. A cooling failure can affect electronics, food, people, and water recovery. A leak changes pressure and consumes stored gas. A false sensor reading can be as dangerous as a bad chemical value because the crew may control the system toward the wrong target. The International Space Station provides decades of operational experience with many parts of this problem. Its environmental control and life support system recovers water from humidity and urine. It uses electrolysis to split water and produce oxygen. It removes carbon dioxide. A Sabatier reactor can combine carbon dioxide from the cabin with hydrogen from oxygen production, creating water and methane. The water can return to the loop. The methane is released in the current station configuration. That is a powerful partial loop. It is not a sealed artificial biosphere. The station receives replacement parts and consumables from Earth. Crews and ground teams maintain hardware. Failed units can sometimes be returned for analysis. New systems are tested where help and resupply remain possible. Mars needs the lessons of the station, but the distance changes the standard. A technology suitable for orbit near Earth may need lower maintenance, better diagnostics, more common parts, more autonomy, and a different failure tolerance before it can support a crew for years. The habitat also has to protect itself from the work the crew came to perform. Every journey outside carries Mars back toward the living space. Martian dust is not merely sand in a red desert. It includes particles fine enough to remain suspended, cling to surfaces, and follow suits and equipment through an airlock. The grains can be abrasive. Dust can reduce the output of solar arrays, alter thermal surfaces, enter joints, load filters, obscure cameras, and challenge seals. The health question is more uncertain than a simple list of minerals suggests. No sample of authentic airborne Martian dust has been returned to Earth. Scientists have rover and lander measurements of soils and rocks. They have remote sensing, meteorological observations, terrestrial analogs, and manufactured simulants. Each source answers part of the question. None reproduces exactly what a person might inhale after repeated surface work at a specific landing site. In July 2026, NASA described a preliminary Martian dust requirement for future crew systems. It limits particles smaller than 10 micrometers in the habitable atmosphere to a 24-hour time-weighted average below 0.1 milligrams per cubic meter, for exposure scenarios lasting up to 30 days. The working group deliberately used a conservative approach because the evidence still contains important gaps. The boundary is useful, and its limit is equally useful. A standard for exposure up to 30 days cannot quietly become proof of safety for a 500-day surface stay. Longer missions need additional evidence, monitoring, and design margin. Chemistry adds another layer. In 2008, the Phoenix lander touched down in the northern plains and delivered soil to its wet chemistry laboratory. The analysis found perchlorate at about 0.4% to 0.6% by mass in those samples. That was a local measurement, not a declaration that every handful of Mars has exactly the same composition. Perchlorate can matter through ingestion and processing, especially if local material enters water extraction or crop systems. The 2026 NASA Dust Review judged several individual constituents to be low inhalation risks under the proposed overall dust limit, while recommending broader management of perchlorate across possible exposure routes. That distinction prevents two errors. Perchlorate is not a magic word that makes all Mars soil instantly poisonous. It is also not something a food and water system can ignore. Mars dust is electrically active as well. In 2025, NASA reported that Perseverance had recorded electrical discharges associated with dust devils. The instrument heard short crackling events and measured electromagnetic effects as grains moved and charged. The discovery matters for atmospheric chemistry and for future equipment design. It does not mean explorers will walk through giant lightning bolts. The actual events were small, and robotic missions have operated on Mars for decades without reported catastrophic discharge damage. The evidence invites grounding, shielding, testing, and monitoring, not spectacle. The best dust solution may begin by refusing to bring the suit into the cabin. Some habitat concepts place suits outside, attached through rear entry ports, so a person enters from the back while most dusty surfaces remain beyond the pressure wall. Airlocks can use zones, brushes, gas flow, electrostatic methods, or cleaning tools. Rovers and work plans can reduce unnecessary exposure. Filters and particle sensors can reveal what still enters. Each measure spends something. A suit port adds seals and mechanisms. Cleaning spends crew time, power, gas, filters, or water. A failed dust control device becomes another item to repair. Avoiding dust may constrain how often the crew can work outside. The contamination system therefore joins the science schedule, power budget, spare parts plan, and life support load. The airlock is not only a door, it is a customs boundary between two worlds. The spacesuit carries that boundary onto the body. A surface suit must hold pressure while allowing a person to bend, reach, walk, use tools, and see the terrain. Every joint is a compromise between mobility and containment. Bearings, fabric layers, seals, visors, gloves, life support connections, radios, batteries, and cooling hardware all experience dust and repeated use. Gloves reveal how a small interface can control a mission. Thick pressure layers resist bending. Hands work against the suit. Fine tasks become tiring. A scratched visor changes visibility. A contaminated seal may not close as designed. A suit that technically contains pressure can still reduce the speed and precision of geological work or repair. Surface planning can protect the suits. Tools can be designed for gloved hands. Equipment can use large capture features and common fasteners. Work can be rehearsed with realistic mobility limits. Delicate service points can face inward toward protected areas. Rovers can carry tools and samples, so astronauts do not carry every load. The suit also creates a miniature consumable budget. It needs oxygen, cooling, electrical power, and carbon dioxide removal for each excursion. A longer walk increases science return, but spends more of those resources and brings more dust back. Emergency reserves limit how far a person can travel from shelter. This is why a distant hill is not merely a destination. It is a round trip inside a smaller survival chain, nested within the larger one. Samples returning from that hill need their own path. Scientific integrity demands protection from contamination brought from Earth. Crew health and planetary protection work may demand controlled handling of Martian material. Glove boxes, sealed containers, cleaning procedures, and dedicated analysis spaces prevent one exciting rock from becoming an uncontrolled source of dust inside the habitat. The rule remains consistent. Mars becomes usable only when its material crosses boundaries through verified processes. Once dust crosses that boundary, water can carry it farther. A particle may be trapped by a filter. A soluble chemical may enter a waste stream. Cleaning can create contaminated liquid. A crop system may need its own separation from material excavated outside. The habitat's loops begin to touch. Water shows most clearly why that connection matters. Imagine one cup entering the crew's supply. Some is drunk. The body uses it, then releases water through breath, sweat, and urine. Cabin air passes over a cold surface, and humidity condenses. Wastewater enters processors. Filters remove particles. Other beds capture dissolved contaminants. A catalytic reactor breaks down compounds that should not remain. Sensors check quality. Water that fails the test passes through again. Clean water returns to storage. On the International Space Station, the addition of a brine processor allowed a particular system configuration to demonstrate close to 98% total water recovery. NASA described the result with a simple example. If the system begins with 100 pounds of water, 98 pounds continue around the loop, and 2 pounds are lost from that accounting cycle. For a station that receives cargo from Earth, even a small annual loss can be replaced. For Mars, the number raises a different question. How many losses can the mission absorb before it reaches a reserve it promised never to use? We can build an intentionally simplified picture. Suppose a closed inventory kept 98% of its water after each complete pass and received no makeup water at all. After one pass, 98% remains. After 10 identical passes, about 82% remains. After 100, only about 13% remains. That is not how a real spacecraft water inventory is operated. Water does not march through one synchronized full system cycle. People carry water in their bodies. Tanks hold reserves. Some uses release water on different schedules. Maintenance can restore performance. Local ice may add supply. The illustration leaves out buffers, timing, and engineering control. Its lesson is narrower and more important. A small fractional loss is not small when the same process repeats without replacement. This is Mars turning reliability into a rate. High recovery still demands energy: filters, pumps, membranes, distillation, heat rejection, microbial control, sensors, calibration, and places to put the material that is not water. Concentrating waste can make the final water harder to recover. Every added percent may require more equipment or more maintenance. A machine optimized for maximum recovery may not be the machine with the best overall reliability. Water quality is as important as quantity. A clear liquid can contain dissolved chemicals, microbes, or products from material degradation. Sensors often measure specific properties rather than proving the absence of every possible contaminant. Electrical conductivity can reveal some dissolved material. Other detectors target organic carbon or selected compounds. Periodic sampling and multiple treatment barriers reduce the chance that one failed sensor declares unsafe water clean. Treatment can create its own byproducts. Filters concentrate what they remove. A catalytic reactor needs the correct temperature and flow. Disinfectants protect storage but must remain within safe levels. Microbes can colonize surfaces that stay wet. Stagnant branches in plumbing can behave differently from the main loop. The crew therefore needs procedures for water that fails a check. It can be routed back through processing, isolated, sampled, or reserved for a use that does not require drinking quality. The system should reveal the problem before the main tank is contaminated. Leak detection also belongs to water. A few drops behind a panel are not only lost inventory. In a warm cabin, they can reach electronics or support microbial growth. In a cold external line, water can freeze, expand, and block flow. Locating and drying the leak may consume more labor than replacing the lost volume. Reserve water has to remain usable. Tanks need materials compatible with long storage. Valves must open after waiting. Quantity measurements have to work in changing gravity. A reserve hidden in shielding cannot be so difficult to access that the crew cannot use it during a failure. These details make the simplified 98% lesson more precise. Loss is not one stream. Some water leaves in waste. Some remains trapped in filters or brine. Some is carried outside. Some leaks. Some is held in food or equipment. Some becomes temporarily unavailable because its quality is uncertain. The system needs to know not only how much water exists, but where it is and what uses it can safely serve. There is no single magic efficiency. Designers have to balance recovery, mass, power, crew time, spare parts, storage, and health risk. They also have to decide what local water means. Orbiters have mapped signs of subsurface water ice across parts of Mars. NASA's Subsurface Water Ice Mapping project combines data from several missions to identify likely ice in the northern mid-latitudes, where temperatures and landing conditions may be more practical than at the poles. Some earlier maps suggested ice could lie within tens of centimeters of the surface in selected regions. A blue patch on a map is not a glass of water. The crew would need to reach the deposit, excavate material, move it, heat or process it, separate water from soil and salts, purify the product, verify its quality, and store it without losing too much. The ground may be harder, dustier, saltier, deeper, or less uniform than the orbital estimate suggests. Excavation equipment has its own seals, bearings, blades, power demands, and spare parts. Local ice can transform a mission if it is accessible. It can also create a new chain on which the mission depends. A responsible architecture asks, what happens if production reaches only half its target? If a drill fails, or if the best ice lies farther from the habitat than expected? Water is both shield and supply. Tanks placed around occupied areas can add radiation protection. Water feeds oxygen production. Water supports hygiene, medicine, food preparation, and crops. It can contribute hydrogen for chemical processes and, in some architectures, propellant production. This makes water valuable enough that no single tank level tells the whole story. Moving it toward one use changes margins somewhere else. By the time one cup has completed the loop, it has touched nearly every system in the habitat. Air is even less willing to remain inside one chapter. A sealed cabin does not preserve a healthy atmosphere merely because its walls do not leak. People continuously change the mixture. They consume oxygen and release carbon dioxide, heat, humidity, odors, particles, and trace chemicals. Equipment adds heat and compounds from materials. Cleaning products and experiments contribute their own chemistry. Microbes live on skin, in bodies, on surfaces, in water, and in filters. The life support system has to keep all of this moving through safe ranges. Oxygen receives most of the attention because its absence acts quickly. But too much oxygen can change fire risk. Pressure controls how gases move through lungs and how suits and structures are designed. Carbon dioxide can form local pockets if ventilation is poor, even when the average cabin reading looks acceptable. Humidity affects people, condensation, electronics, and microbial growth. Trace contaminants can accumulate slowly. A filter that works perfectly until it saturates is not a permanent solution. The simplest drawing of air revitalization looks like a loop. Crew breathe out carbon dioxide. A machine removes it. Another machine makes oxygen. Arrows return clean air to the cabin. The real system has edges. On the station, electrolysis splits water into oxygen and hydrogen. The oxygen enters the cabin. Hydrogen can react with captured carbon dioxide in a Sabatier process to create water and methane. Some water returns. Methane leaves the current loop. Other carbon dioxide may be vented. Nitrogen and other buffer gases can be lost through leaks, airlock operations, or maintenance. Filters and sorbent beds eventually need service or replacement. A Mars system may close more of those edges, carry more reserves, or accept selected losses. The correct answer depends on the mission. Perfect closure can be an expensive target if the equipment needed to recover the final fraction weighs more, consumes more power, or fails more often than a carefully calculated reserve. But carrying all consumables from Earth also drives mass and landing requirements. This is why a habitat is best understood as a managed ecosystem joined to a chemical plant. The ecosystem does not have to look like a forest. In early missions, it may rely heavily on physical and chemical machines with a smaller role for plants or microorganisms. Machines are easier to start, stop, test, and model than a large biological community. Biology can regenerate resources, produce food, improve variety, and support crew well-being, but it also responds to light, temperature, nutrients, microbes, and gravity in ways that create new uncertainties. Microbes demonstrate the trade. A completely sterile, crude habitat is impossible. Human bodies carry vast communities. The goal is to keep the cabin community within safe and useful bounds. Surfaces can be cleaned, air and water can be filtered and treated, sensors and samples can identify changes. Materials can be chosen to resist growth, but microbes also evolve, exchange genes, form films, and occupy inaccessible spaces. A biofilm inside a wet line is not merely a health concern. It can change flow, block a sensor, corrode material, or contaminate a water sample. The medical system, plumbing system, and maintenance system become the same problem viewed from different sides. Fire creates another coupling. Earth buildings can open windows, evacuate occupants, and call firefighters. A Mars habitat cannot vent smoke and wait outside. Fire detection must find an event quickly. Ventilation that normally keeps air safe can also move smoke. Extinguishing agents must work in the chosen atmosphere and cannot create a second lethal condition. Afterward, the crew must identify damaged wiring, remove contaminants, and decide whether the affected volume can be used again. The strongest design is not one that promises nothing will fail. It is one that notices failure early, prevents one event from taking the whole system, and gives the crew a way to recover. That principle is called graceful degradation, when a system loses some capability without collapsing completely. In ordinary life, a building can lose one elevator and continue operating. On Mars, a life support assembly might lose one processing path, while a backup carries a reduced load. The crew may suspend a water-intensive experiment, limit an outside activity, change a food plan, or isolate one cabin. Mission objectives can be traded to protect survival. This sounds like retreat only if success is defined as following the original schedule. A distant crew needs a hierarchy. Preserve life. Preserve the habitat. Preserve the ability to leave. Then preserve the science that remains compatible with those promises. Food sits high in that hierarchy because people cannot postpone nutrition for years. The popular solution is a greenhouse. The image is irresistible. Green leaves under warm lights, astronauts harvesting tomatoes, oxygen rising from plants, water returning through roots, waste becoming fertilizer. Some of those processes can genuinely support exploration. Plants can supplement diets, produce fresh food, contribute to atmosphere and water cycles, and provide sensory variety in a metal habitat. The image becomes misleading when it hides scale and risk. Plants need light, water, carbon dioxide, nutrients, appropriate temperature, space, and labor. Electric lights convert power into photons and also create heat that must be removed. A crop disease, failed pump, nutrient imbalance, or pollination problem can affect an entire harvest. Edible mass is only part of plant mass. Growth takes time. Different crops provide different nutrients. A greenhouse that produces an enjoyable salad does not necessarily provide the calories, protein, fats, vitamins, and minerals for a complete crew diet. Early Mars missions are therefore likely to depend heavily on stored food, even if they grow selected crops. Stored food has its own mission clock. Some cargo may launch years before the crew eats it. NASA's food program studies exploration meals that remain safe, nutritious, and acceptable for up to 5 years. Safety is only the first condition. A sealed meal can remain free of dangerous microbes while vitamins slowly degrade, texture changes, flavors decline, or oxidation reduces quality. Acceptability is not decoration. People must consume enough of the food to maintain health and performance. Repetition, appetite changes, workload, illness, and individual preference all influence intake. A meal with perfect laboratory nutrition has failed if the crew consistently cannot eat enough of it. Menus also interact with water and waste. Freeze-dried foods save some mass but need water for preparation. Thermostabilized foods carry their water with them. Packaging shapes storage volume and trash. Crumbs and powders can enter ventilation. Strong odors can linger in a closed cabin. Preparation equipment consumes power and has to be cleaned. Crew members may eat differently during heavy work, illness, or adaptation to gravity. A food system sized only around an average day can miss the periods when health recovery requires more. Nutrition planning, therefore, uses margins and variety rather than one perfect repeated ration. Crops create time-sensitive inventory. Seeds can wait, but once a crop starts, light and water interruptions matter. Plants release humidity. Roots and nutrient solutions host microbes. In Mars gravity, fluid and gas behavior will differ from both Earth and microgravity, and long-duration crop systems at that gravity remain untested with people. The safest early role for crops may be supplemental. A failed harvest then removes variety and some nutrients without removing the crew's entire calorie supply. As evidence and reliability grow, biology can carry more of the burden. This is how a settlement grows honestly. It does not begin by declaring independence. It earns independence one closed, repairable function at a time. Packaging protects food but adds mass and waste. Refrigeration can slow chemical change but consumes power and hardware. Pre-positioning food reduces the mass that travels with the crew, but it increases storage age and asks an uncrewed system to maintain the correct conditions before arrival. Nutrition can also be produced in smaller, more targeted ways. NASA's bionutrients experiments have tested engineered microorganisms that make selected compounds on demand. The idea responds to a precise problem. Vitamins, including B1 and C, can degrade over long storage, so a small biological factory might produce a needed nutrient later in the mission. That does not turn a powder packet into dinner. It shows how a mission can close one vulnerable part of the food system without demanding that one greenhouse replace every meal. The distinction is useful across Mars planning. A technology can solve a bounded function and be extremely valuable. Trouble begins when a successful function is silently expanded into a whole system. MOXIE made oxygen. It did not fill an ascent tank. A crop experiment grows food. It does not feed a crew for years. A water recovery demonstration reaches 98%. It does not remove maintenance or every loss. A radiation measurement guides shielding. It does not select the final vehicle. This is not a list of reasons to doubt progress. It is how progress becomes reliable. A demonstration says one link can work. Architecture asks whether all necessary links can work together at the required scale for the required time. NASA uses Earth analogs to study some of the human and operational links. The first Chapeya mission placed 4 volunteers inside a 1,700 square foot habitat for 378 days. They carried out simulated surface work, maintenance, exercise, crop cultivation, and other tasks under resource limitations, isolation, and delayed communication. The habitat stood in Houston. It could not reproduce Mars' gravity, deep space radiation, real dust, or the knowledge that Earth was physically unreachable. That limitation does not make the experiment useless. It defines what the data can answer. Chapeya can reveal how schedules, food systems, workload, team processes, maintenance demands, and resource constraints interact in a long, controlled campaign. Other facilities and space missions answer different parts. The complete Mars problem cannot be reproduced in one place on Earth. It has to be assembled from evidence with visible seams. Those seams will demand power. Every loop we have followed draws electricity. Air has to move. Carbon dioxide has to be separated. Water has to be pumped, heated, distilled, pressed through membranes, and checked. Food may need cold storage or lighting. A suit has batteries and cooling. A rover moves people and equipment. Communication systems point toward orbiters or Earth. Computers monitor the habitat. Tools manufacture or repair parts. Oxygen production compresses thin Martian air and heats electrochemical components. Power is not another appliance in the habitat. It is the condition that allows nearly every appliance to exist. Solar energy is proven on Mars. Landers and rovers have used panels for decades. The surface receives less sunlight than Earth, and dust in the atmosphere and on panels can reduce output. Seasons, latitude, terrain, and weather change the available energy. Batteries or other storage must carry essential loads through darkness and low production. Arrays for a crew base would be much larger than those on a rover, and deploying, cleaning, connecting, and repairing them becomes surface work. Nuclear fission offers a different profile. NASA's fission surface power work targets a small system capable of producing up to 10 kilowatts continuously for at least 10 years. Program descriptions have used 4 such units as an illustrative scale for robust operations on the Moon or Mars. The work is real. A Mars installation is not. Fission can produce power through night, dust, and winter. It also requires launch approval, heat rejection, shielding, deployment distance, cables, control hardware, and maintenance planning. Solar arrays avoid a reactor, but create a larger dependence on variable light and energy storage. A mission can combine sources. The right mix depends on site, loads, risk tolerance, and the systems that absolutely cannot go dark. The phrase "absolutely cannot go dark" deserves suspicion. No practical power source is beyond failure. A robust architecture divides loads by priority and allows the system to shed non-essential work. Science equipment can turn off. A greenhouse may reduce lighting. Resource production can pause if stored reserves permit. Habitat pressure control, carbon dioxide removal, temperature protection, communications, and medical functions receive higher priority. This is another form of graceful degradation. The base becomes smaller in capability before it becomes unsafe. Redundancy helps, but simply carrying two of everything is not enough. The two units may share a design flaw. They may need the same controller, coolant, filter, or software. They may sit beside one another and face the same fire, dust intrusion, or electrical surge. True resilience asks how failures are related. Power distribution deserves the same attention as power generation. A healthy reactor or solar field cannot help if a cable is severed, a connector overheats, or a controller refuses to route current. Long cables across the surface create mass, voltage loss, deployment work, and damage exposure. Burying or shielding them protects against some hazards and makes inspection harder. The base may use a direct current network with converters for different equipment. Batteries smooth changing loads and provide emergency energy. Switching hardware separates faults. Software schedules large users, so an oxygen plant and a greenhouse do not start at the same moment and pull the network below a stable limit. Heat is the companion flow to electricity. Nearly every watt used inside eventually becomes heat that must go somewhere. A fission unit creates heat even beyond the electricity delivered. Batteries and power electronics have temperature limits. Cables heat under load. Radiators must reject energy while surviving dust and cold. An energy budget that counts generation but ignores heat rejection is incomplete. Maintenance planning can use the shape of the network. Essential loads may have two physically separated feeds. Local batteries can keep a valve or communication node alive through a central outage. Manual connections can bypass failed automation. The crew can see which loads are drawing power and why. Visibility matters because a base cannot afford mysterious consumption. A drifting heater, clogged pump, or failing bearing may first appear as a small increase in electrical demand. Trend data can reveal the change before the device stops. Predictive maintenance turns watts into evidence. A spare pump is useful if the crew can reach it, install it, connect it, test it, and understand why the first pump failed. A box labeled spare has no value if the matching tool was lost, the seal aged, the software refuses the replacement, or a deeper problem destroys the new unit. This makes maintainability a scientific discipline of its own. Engineers can design common interfaces so one component serves several systems. They can place high failure items where gloved hands can reach them. They can include isolation valves, test points, bypass lines, and manual controls. Software can compare sensors and identify inconsistent readings. Digital procedures can adapt to the hardware configuration that remains. Additive manufacturing may produce selected tools, ducts, brackets, or seals, but a printer cannot create every alloy, electronic chip, lubricant, sensor, or sterile medical item from raw dust. The most valuable spare may be information. A good diagnostic can keep the crew from replacing the wrong component. A failure history can reveal that 3 sensors changed together because their shared power supply drifted. A physical sample can be compared with an onboard database. A camera can send images to Earth for a slower expert review. Yet information also has a clock. When a warning indicates a fast pressure loss, rising carbon dioxide, smoke, or overheating battery, the crew cannot wait 44 minutes for a complete exchange with Earth. The vehicle must make safe states obvious. People must train on principles, not only scripts. Training for principles means understanding the physical system beneath the procedure. If a pump stops, the crew should know what the pump was moving, what can overheat or accumulate, which valve isolates it, how long the buffer lasts, and what loads can be reduced. A checklist remains valuable, but the event may not match the checklist's exact assumptions. Onboard simulation can help. A digital model can compare expected pressures, temperatures, flows, and electrical loads with actual sensor data. If several readings change together, the model can suggest shared causes. The crew can test a proposed valve sequence against the model before applying it to the real habitat. Models also fail. A sensor can lie in a way the software does not expect. A physical blockage can behave differently from its mathematical representation. The system needs independent measurements and people who can ask whether the model's story fits what they hear, see, smell, and touch. Smell is a real detector in a cabin, but it is neither precise nor safe to rely on. A hot electrical odor may direct attention. It cannot measure a toxic compound. Humans add context to sensors. Sensors add reach and quantification to human judgment. Medical autonomy works the same way. Earth physicians can review images, records, and trends, then send advice. The crew handles immediate stabilization and decides what information to collect. Communication delay encourages structured messages. What happened, what was measured, what treatment was given, and what changed can travel as one package rather than a slow series of questions. The habitat can also carry a digital medical history and decision aids that work without a live link. Privacy and access matter. So does the possibility that the event affects the person with the most training. Cross-training turns the team into a network instead of a single point of failure. Supplies require an expiration strategy. Some medicines degrade. Some tests need reagents. Sterile packaging can fail. A mission cannot carry a complete terrestrial pharmacy, so it chooses broad usefulness, stability, and the conditions most likely to threaten life or performance. Future on-demand manufacturing may help with selected compounds, but it must meet purity and dose requirements before it becomes medical capability. The most important medical action may be changing the mission, delaying a surface excursion, reducing workload, isolating a crew member, or returning early within an available window can protect the whole team. That decision joins health evidence to trajectory and consumable margins. Autonomy is therefore not heroic independence. It is the disciplined ability to make bounded decisions with incomplete help, then explain those decisions when the answer from Earth arrives. Mission control becomes something different across that distance. It remains a vast source of expertise, planning, simulation, and second opinions. It can study trends over hours and days. It can build and test a repair on Earth, then send instructions. But during a fast event, it is a consultant whose message is still traveling. This shifts authority into the habitat. The crew needs permission structures that do not require Earth to approve every necessary action. The onboard software needs boundaries that prevent an automated response from creating a worse condition. Medical care needs decision support, imaging, drugs, instruments, and crew training suited to problems that cannot be evacuated to a hospital. The human pressure is not simply loneliness. It is the combination of isolation, workload, risk, limited privacy, recurring maintenance, delayed family communication, and the knowledge that the same small group must keep making decisions together. Teams can train for conflict, communication, leadership transitions, and fatigue. Schedules can protect sleep and recovery. Private space matters. Meaningful work matters. So does admitting that analog studies cannot perfectly reproduce the psychological reality of Mars. We should not invent a crew argument to make this vivid. The real operational fact is stronger. Every unresolved interpersonal problem consumes attention from a system with no replacement staff. Every good team practice preserves a resource that cannot be packed in a tank. At this point, the Mars habitat begins to look less like an outpost and more like a small, independent city. The comparison is still too generous. Cities receive food, water, parts, workers, and emergency support from larger networks. A first Mars habitat has perhaps 4 people and a collection of machines surrounded by a planet that cannot supply a breath until those people successfully process it. Independence, therefore, cannot mean isolation from Earth. It means delaying the need for physical help beyond the mission's return date. That return date may depend on the moment when a resource on a map becomes a verified quantity in a tank. Mars offers carbon dioxide almost everywhere in its atmosphere. It offers water ice in many regions, including deposits mapped beneath the surface at northern mid-latitudes. Sunlight reaches the ground. Regolith can provide bulk mass and perhaps useful chemical feedstocks. None of those resources arrives purified, connected, or certified. Resource use begins with knowledge of a site. Orbital instruments infer ice through temperature, radar, neutron measurements, fresh impact exposures, and other evidence. A map combines those observations into a best estimate. A lander can then drill, heat, image, or chemically analyze local material. Only direct work at the site can reveal the exact depth, hardness, contaminants, and extraction behavior encountered by the equipment. This creates a ladder of certainty. The ladder also changes the order of exploration. Robotic precursors can survey a site before the crew. A lander can measure the mechanical strength of soil, the size distribution of dust, seasonal pressure, radiation, and the depth of ice. A pilot plant can run through a full Martian year. It can expose seals and filters to real cycles and show how much maintenance an autonomous machine requires. Such a precursor is not glamorous compared with a human landing. It can remove an entire class of uncertainty from the crew's mission. If a production rate falls every winter, planners can enlarge storage, add power, change the site, or abandon that process before human life depends on it. Verification needs more than a status bit. A tank can report a pressure that appears correct while containing the wrong temperature, phase, or mixture for the intended burn. Independent sensors can measure quantity and quality through different physical methods. Samples can be analyzed. The system can perform a controlled test. Data trends can reveal slow leaks. The word independent is important. If two displays use the same failed sensor, agreement proves nothing. Redundant measurements should avoid hidden common causes where the consequence justifies the mass. Resource plants must also survive the transition from production to standby. A machine that runs continuously may not restart after months off. A tank kept cold during production must remain cold while other surface work changes the power schedule. The ascent vehicle may require periodic checkouts that consume a small amount of stored propellant or pressurant. This is why mission success cannot be assigned to the day a target amount is first reached. The mission needs the amount to remain usable until departure. At the first rung, the resource probably exists in a region. At the next, instruments verify it at a landing site. Then equipment extracts a sample. A processing system produces clean water or gas. Storage holds the product. Repeated operation proves a rate. Maintenance proves that the rate can continue. Finally, the mission accumulates enough verified reserve to use the resource for a life-critical purpose. Skipping a rung does not make the chemistry false. It makes the promise premature. MOXIE reached an extraordinary rung for atmospheric oxygen. It operated on the Martian surface, across different seasons and times of day. It pumped the thin carbon dioxide atmosphere inward, compressed it, heated a solid oxide electrolysis stack, separated oxygen atoms from carbon dioxide molecules, measured the product, and released the gases. Across its campaign, it showed that the process could start and work under actual Mars conditions. The next machine would have a different job. It would need much greater production, longer operating life, storage, fault detection, repair, and integration with power and an ascent system. NASA has described a crew-scale generator as roughly 100 times larger than the MOXIE test model in broad planning terms. Scaling production is not only enlarging the electrolysis stack. Compressors, filters, heat exchangers, seals, insulation, tanks, valves, and power electronics all scale or multiply. Storage can be as difficult as production. Oxygen intended as rocket oxidizer may be liquefied, which demands very low temperature. Heat leaking into a cryogenic tank can boil liquid into gas. A tank can vent some gas to control pressure, but every vent is lost propellant. Insulation, shade, active cooling, and tank geometry become part of the return budget. The system must also know how much usable liquid is truly present. Methane adds another branch. A Sabatier process can react carbon dioxide with hydrogen to make methane and water. Mars provides the carbon dioxide. The hydrogen may come from water. That moves the problem toward ice extraction and electrolysis. A methane and oxygen ascent system could therefore turn local air and water into much of its propellant. But it also joins two resource chains that must both work. Some architectures reduce risk by carrying methane or all propellant from Earth. That increases launch and landing mass. Other architectures produce oxygen locally because oxygen forms most of the propellant mass in many methane engine mixtures. A mission can send the plant before the crew, allow it to operate for months, and launch people only after instruments confirm that the tanks are full. That last choice is one of the clearest examples of designing the return before departure. Imagine two status lights in mission control. One indicates that a habitat on Mars is pressurized, powered, and stocked. The other indicates that the ascent propellant has been produced, stored, sampled, and independently measured. The crew does not leave Earth because engineers believe those systems will probably work later. They leave after Mars reports that the path home already contains real margin. Even then, local production creates duties throughout the surface stay. A long-stored propellant tank has to remain healthy. Valves may need cycling. Temperatures and pressures need trends, not single readings. Dust cannot be allowed to choke an intake. Power interruptions must not damage the plant or spoil the product. The crew may need to repair a system that was designed to reduce the mass they carried. This is why a resource is not free mass. It is exchanged mass. The mission carries less water or propellant, but it carries excavators, compressors, reactors, radiators, cables, spares, instruments, and uncertainty. The trade can still be strongly favorable. It simply has to be calculated across the whole chain. The same logic applies to regolith shielding. Covering a habitat with local soil can reduce the shielding mass launched from Earth. It requires excavation and material handling. The habitat structure must support the load. Airlocks and radiators must remain accessible. Dust control must protect machinery and crew. Construction has to finish before the radiation benefit is fully available. Local material becomes valuable through reliable work. Now the return morning arrives. The phrase sounds precise, but the vehicle has been approaching it for years. Its tanks may have crossed interplanetary space before the crew. Its engines may have waded through thousands of temperature cycles. Dust may have settled around mechanisms. Radiation may have affected electronics. Seals may have aged. Sensors may have drifted. Software may have received updates. The crew may have serviced components, sampled propellant, tested valves, and rehearsed procedures many times. On Earth, a launch vehicle is assembled and inspected by a large organization. Teams replace suspect parts. Weather officers monitor conditions. Range safety systems protect surrounding communities. Engineers sit with live telemetry. Emergency crews wait near the pad. On Mars, the launch team is also the passenger list. Current NASA architecture work still compares whether a lander and ascent vehicle should be one system or separate vehicles. A combined vehicle could avoid transferring the crew across the surface, but it asks one structure to survive entry, landing, a long stay, and ascent. A separate ascent vehicle can be optimized for departure and perhaps checked before the crew arrives, but the crew must reach it and transfer into it safely. Whatever the design, ascent begins under Mars gravity and inside Mars' atmosphere. The atmosphere is thin, so aerodynamic drag is lower than on Earth, and Mars' escape speed is lower. Those are real advantages. But an engine failure remains an engine failure. Guidance has to place the vehicle on an orbit where it can reach the next element of the return system. If a separate transit vehicle waits in Mars' orbit, timing and navigation must bring them together. The vehicle's small size compared with an Earth launch system can be deceptive. It may not need to escape directly to Earth. It may only need to deliver the crew and samples to orbit, where a larger vehicle provides the return burn and months of habitation. That division reduces ascent mass, but it makes the orbital rendezvous essential. An ascent stage needs more than fuel and an engine. It needs tanks, pressurization, valves, ignition, guidance, navigation, control, communication, electrical power, thermal protection, structure, and a cabin or protected crew volume. If propellants are cryogenic, their condition must remain correct. If the engine has waited unused, checkout data has to provide confidence without consuming the limited life of the hardware. Mars weather may influence launch operations through dust, winds, temperature, and atmospheric density, though the exact limits depend on the vehicle. The crew needs forecasts from surface instruments and orbiters. A launch window for rendezvous can be narrow. Waiting for better local conditions spends surface consumables and changes the orbital geometry. Samples create another trade. Returning more material can transform science, but every kilogram needs ascent performance, containment, storage, and Earth return planning. Scientific ambition sits behind crew safety and vehicle margin. Once the ascent burn starts, options narrow quickly. An Earth team watches delayed telemetry that describes events already completed. Onboard guidance must detect problems and use whatever contingencies the architecture provides. The crew may have limited control, but there is no giant ground team physically connected to the pad. The launch is a test of all the invisible preparation: a correct bolt, a clean seal, a charged battery, a calibrated inertial unit, a stable propellant, and a healthy crew become one event. Rendezvous is familiar in Earth orbit. Crews and cargo vehicles have performed it many times. Mars changes the support environment and the consequences of missing. The orbiting vehicle has its own power: thermal, life support, propulsion, and maintenance clock. It may have waited uncrewed. The ascent vehicle and orbital vehicle must communicate, track, approach, and dock. A failed docking mechanism can strand two working spacecraft a short distance apart. This is the point where every earlier movement converges. The crew must be healthy enough to enter the ascent vehicle, tolerate acceleration, monitor systems, and respond. The habitat must preserve them until the last planned moment. Power must keep propellant in condition. Dust control must protect seals and mechanisms. Navigation must know the vehicle's state. Communication delay means Earth cannot fly a rapidly changing event by hand. Food and water reserves must cover delays. Spare parts and repair work must have preserved the right components, not merely the most obvious ones. The ascent engine does not erase those systems. It caches the margin they preserved. When the vehicle lifts, Mars finally sees something no mission has attempted before. A machine rises from the surface toward orbit. That achievement would be enormous. It would still not be home. The crew must join the return vehicle, configure it, and leave Mars. The trajectory back to Earth can last months. Galactic cosmic rays continue. Solar events remain possible. Life support keeps cycling. Food keeps aging. Machines keep accumulating operating time. The body returns to microgravity after adapting to Mars gravity, then prepares for a full Earth gravity field. Earth entry is a final conversion of speed into heat. The vehicle must protect the crew, control its path, deploy recovery systems, and reach a location where teams can help. A person who has spent years away may experience dizziness, weakness, balance difficulty, or problems maintaining blood pressure when standing. Medical teams can be ready on Earth in a way they never could be on Mars. That contrast reveals the real boundary of the mission. Rescue becomes available again only near the end. Before asking what might fail first, notice what a serious test program would have to prove. A pump can pass a laboratory endurance run while the habitat around it is missing. A water processor can reach its target recovery while the waste path, heat rejection system, maintenance schedule, and crew workload remain represented by test equipment. An ascent engine can fire successfully without spending years beside Martian dust, cold, stored propellant, and a power network that serves a living base. Those tests are still valuable. They isolate mechanisms and expose weaknesses. But a round-trip architecture needs another layer of evidence at the seams. Engineers can connect flight-like subsystems and run them through long campaigns in which ordinary changes are allowed to accumulate. Filters load, sensors drift, software updates. A planned maintenance task takes longer than expected. A food system changes the water demand. An exercise period raises cabin heat and humidity. A dust control cycle consumes power at the same time a resource plant wants to compress gas. The purpose is not to stage a cinematic disaster. It is to discover whether small, believable disturbances coordinate themselves into a condition the design did not anticipate. The most revealing rehearsal may be the one that ends safely after losing part of the mission. A crop chamber is shut down to protect life support. A surface journey is delayed to preserve a repair window. Oxygen production pauses while a shared cooling path is serviced. The crew uses a reserve, identifies why it was needed, and restores margin before the next commitment door closes. That is how graceful degradation becomes evidence rather than a phrase. The system demonstrates that it can become smaller without becoming unrecoverable. No Earth test can reproduce Mars completely. Gravity, radiation, dust, distance, and mission duration resist being placed in one facility. The answer is not to pretend that the missing environment does not matter. It is to keep the seams visible, combine tests that answer different questions, and refuse to promote a component result into a mission result without showing the path between them. The first crew will still enter uncertainty. The aim is to make that uncertainty bounded, measured, and attached to fallback paths that were exercised before human life depended on them. So what would fail first on Mars? There is no scientifically honest component we can name. No human Mars architecture has flown. The vehicle designs remain open. Sites differ. Mission classes differ. A short surface stay and a 500-day stay place different burdens on food, dust control, health, and power. A mission that carries all propellant makes different bets from one that manufactures oxygen. A solar-powered base has different common failures from a fission-powered base. The crew, maintenance plan, redundancy, and margins change the answer. Choosing one failure for dramatic certainty would hide the central result. The Mars problem is not that every subsystem is equally fragile. It is that their margins are coupled. If power falls, water recovery may fall. If water recovery falls, reserves shrink, and oxygen production may be constrained. If dust increases filter load, maintenance time and spare consumption rise. If food loses nutritional quality, health and work capacity can decline. If radiation shelter mass increases, vehicle mass and transit design may change. If transit time changes, food age, dose, and component life change. If the crew cannot repair one valve, a tank full of propellant may become unusable. The mission is a web, but it should not be designed like one. In a web, a disturbance can travel everywhere. A resilient architecture inserts boundaries. It isolates faults, carries buffers, diversifies power, shares parts where sharing helps, separates systems where common failure is dangerous, and keeps enough capability to retreat from science before retreating from safety. This gives us an honest answer to the title. We can describe trajectories that reach Mars. We have landed complex robots. We have measured the radiation on the way and on the ground. We recycle most water on the space station. We grow plants in orbit. We have made oxygen from the Martian atmosphere. Engineers study human-scale landers, power systems, habitats, resource plants, ascent vehicles, and return propulsion. The unsolved work is turning those successes into one chain that remains recoverable for years. Getting home is the real mission, because the return vehicle is where every promise comes due. It requires a crew whose bodies can still perform, a habitat that kept them alive, a power system that preserved essential loads, a water and air system that controlled loss and contamination, food that remained nourishing, dust that stayed below safe limits, decisions made without instant help, and propellant that exists as a measured quantity rather than a hopeful resource. The first footprint will be remembered. The first ascent from Mars may be even more astonishing. But the deeper achievement will be quieter. It will be the proof that a handful of people can carry a small living world away from Earth, keep it functioning through thousands of ordinary days and interventions, place it on another planet, and still preserve a continuous line back to the world where every human life began. Mars does not only ask whether we can cross the distance, it asks whether our machines can keep promises for longer than anyone can come to help. The answer is not known yet, but we now know what the answer must contain. Not a single perfect machine, not a dramatic cure for one hazard, not a colony rendered before its plumbing exists, a measured radiation budget, a body that can still work, a landing system proven at the needed scale, a pressure vessel that manufactures safe air, water losses that remain inside real reserves, food that keeps its nutrition, dust control that is designed from the suit inward, power that fails in stages instead of all at once, repairs that the crew can actually perform, resources that become verified products, an ascent system waiting inside the right orbital geometry. and enough honesty to label what Mars gravity, long exposure, and an unflown architecture have not yet taught us. That is more than survival. It is a round trip designed as one idea. And only when the crew is back beneath Earth's sky will reaching Mars be complete.